Okay, so for this loading, so we've got a 6 metre span, we've got a UDL load, and that could be made up of either the dead load, which could be a concrete floor, or the live load. But we don't know what that is. We've been told that we have a beam of 457 by 152 times by 52. So it's a universal beam, or a UB. UB for universal beam, UC for universal column. We're told what the maximum stress is within the steel beam. We're given the A value for steel, and we're told our allowable deflection span over 360. So you can find all of the details within the table. So we have, it's this beam here, and we can pick off our second moment of area. What we're going to do in this example, we're going to use our elastic modulus, the Z. Can anyone remember what the formula is for Z? I over Y. It's, well, you know, if you're ever stuck, then hopefully I've remembered to give you the handout. So you've got Z is I over Y. You've also got a formula where you've got the internal resistance M equals stress sigma times by Z. So this example is just using the elastic modulus, but you could use the second moment of area, your I value, and then your Y. Remember, your Y is the distance from the neutral axis to the furthest point. So within the tables, it usually gives you everything within centimetres. So I've put everything in millimetres here. So our Z is millimetres cubed. Our I value is millimetres to the 4. So that's from the section tables. So there's two things we need to consider for this example, and I'll split the page in half. So we've got our ultimate limit state. So this is where you're looking at the strength, and we're going to look at the stress within the actual beam itself. And secondly, we're going to look at the serviceability limit state. So we're going to look at the deflection, where we've been given an allowable deflection of span over 360. So might as well put that in. Allowable equals span over 360. It's 6 meters long. So we're allowed 17 millimeters. Looking at the tables at the back, so we've got a simply supported beam with a UDL. Our actual deflection is 5WL cubed with 384 EI. The question is, what is W? What can we work out? So if we let our actual deflection equal the allowable. So we'll have 17 equals 5WL cubed over 384 EI. If we rearrange that and put in all of our values, so we end up with our W so what have we got? We've got our 17 millimeters. Bring the 384 up. Next we look at our A value, which is 205 kilonewton per millimeter squared. So put everything into millimeters. Then our I value is 213.7 times 10 to the 6. So that's our deflection. That's 384 constant. That's our A value. That's our I value. All divided by, bring the 5 down, and then bring our L down. Our span is 6 meters. So we found out, based upon the deflection, our beam can take 265 kilonewtons. If you want to be a little bit accurate, it would be 264,798 newtons. Any more than 265, then it's going to deflect further than our allowable of 17 millimeters. Now what we'll do, we'll have a look at the W value based upon the strength of the material. So in terms of working out our W, if we look at our table at the back again, so for a simply supported beam, we've got our maximum moment is WL over 8, or small w L squared over 8. That's our maximum moment. So you're not expected to work out what the moment is. So moment for a UDL is WL squared over 8. You're not expected to work out it from first principles by taking moments around a particular point. So that will give us our maximum moment. Then you've got your moment of resistance of the beam. This is another formula on your exam handout. M equals stress times by Z. I think we did this about a few weeks back. That's your moment of resistance. So we'll let M equals the moment of resistance. So we'll end up with a WL squared over 8 equals stress times by Z. Rearrange them so that we have our W. So we got our W. Remember that it's a small w this time, so I tend to make mine nice and curly, so it's easy to spot in between that and the capital W. Stress times by Z times by 8 over L squared. And if I put everything into newtons and millimeters, so from the question, the stress of the steel is 165 newtons per millimeter squared. My Z value, which I've got from the tables, is 950 times 10 to the 3 millimeters cubed, times by that constant 8, and divided by our L, so it's 6 meters squared. So our UDL is 34.8 kilonewton per meter. That's a UDL. Because you've got small w is large W over L, our large W is 209 kilonewtons. You compare these two values. The safe total load is 209 kilonewtons.